Greetings and welcome to another installment of QuantSlob. This is 10 in our Foundational Series. Now that we've had some watch-outs and discussion around mathematical and scientific terminology, and because we're soon going to need it, this time around we're going to take a quick peek at mathematical functions, their notation, and how they're used. One of the reasons that math is regarded as the language of science is because scientists are keenly interested in how things are related. Mathematics provides the tools for expressing relationships. The mathematical equality, area equals width times height, we looked at previously in the series, expresses a relationship between a rectangle's area and its width and height. It is general as it's true for any rectangle, no matter what the dimensions. Expressing relationships such as area equals width times height as functions allows for even greater generalization and oftentimes even more compact representation. So here we go. Let's break down what we're looking at here. The letter F is the name or a placeholder of our function. The parentheses are what we're calling here on QuantSlob the enclosure. The stuff inside the parentheses, in this case the W and the H, are the function's arguments or inputs. In this example, areas are function's output or value. So we could say that our function F returns a value of area. Except for constants like pi or the number 3, or any other fixed number, the arguments of a function are the only inputs the function requires. In our example, the area of a rectangle depends only on its width and height. Doesn't depend on anything else. What we had for breakfast or how fast we drove our car or rode our bike this morning. Functions provide for high generality. We already said that. To illustrate, I want to consider a question. For what geometric shapes is it true that area is a function of width and height, or the simpler case, area is a function of height? Well, we already know from previous in the series that about the rectangle, and we also know about the triangle, and the ellipse as well. We sort of introduced that too, provided it's true, provided we're measuring the axes. But it turns out the list goes on and on. It includes a parallelogram, it includes an isosceles trapezoid, and in fact it includes any regular polygon, so-called regular polygon. And depending on how liberal we are with assigning parameters, many more 2D shapes. The point here is that when we placehold a function in this way with defined inputs and value, we can refer to a broad constellation of relationships. Lastly, speaking of parameters, commas are used to separate variable arguments in a functions, but sometimes we see a little semicolon sneak in there. Practically, it doesn't matter. The idea, I think, is primarily cosmetic. It's to set apart or distinguish different variable groups, or in a related sense, to denote a function parameter as opposed to a variable input. In this case, we've let the reader know here that A is a parameter, and the suggestion, anyway, is that for one thing, by explicitly fixing A to some value, we can create, for example, a sequence of functions. And that's it. That's going to do it this time around. Thank you so very much for tuning in, and don't forget to stay tuned for more QuantSlob.